So it's my pleasure to introduce our next speaker. Mark Miner is an associate professor at the University of Utah, where he leads the robotic systems lab. And his research focus is on the design and control of robots with novel embodiments. And as part of that, he explores the use of extended reality interfaces for controlling and interacting with them.
All right. Well, thank you for inviting me to speak today. It's really a pleasure to be here and learn about all the great things. And it's perfect that I'm following after Professor Chessa. I think our talks actually have a lot in common. So thank you. Good timing. My talk is about extended reality and Miss Teapot, the virtual reality locomotion interface. Let's see. I know for me, I am seeing something different than what you guys are seeing. Let me see if I can make this. There we go. Okay, so our motivation is we really have a lot of users that want to have meaningful interaction in the virtual environments. In our case, they might be subjects or what we're actually calling participants, for example, people with Parkinson's disease or spinal cord injury, physical therapists, people that might be working with those people, as well as emergency responders or emergency trainers. The key is that, a lot of people, they want to have these meaningful physical interactions. For example, if you're a first responder and you really want to train to react to an emergency situation, like an emergency in a chemical plant, what it really means is that you have to be able to have the physical stress of experiencing these things so that when you get to that point where you have to make that decision, you've had the physical taxation to do it. And the same thing with physical therapy, people that want to learn to walk again. For example, if you have Parkinson's disease or a spinal cord injury, having this kind of meaningful physical interaction is important. And you'll see a lot of VR systems now appearing in clinics where people are learning to walk again. So where all this started is actually with something called the Sarcos Treadport. This is a project that I've been collaborating with John Hollerbach at the University of Utah for about 25 years now. It's a cave display system. It has a large treadmill that allows users to navigate through their virtual environment. And there's a horizontal tether that you can see right here that actually exerts locomotion forces on the person. The treadmill also tilts to allow people to experience walking uphill or downhill. And this is the state of the system about circa 97, 98. One of the things we found in our early research was the treadmill tilt didn't matter. In fact, the tether could imitate all the locomotion forces that you'd feel walking uphill or downhill. And in our studies, we discovered that the biomechanics of the person, the kinematics of the legs, hips, and so forth were actually similar to walking on the treadmill versus actually walking on an inclined surface. So from there, we tried to make the system more immersive. We created something called the Treadport Active Wind Tunnel, or the Treadport. And the idea was, here's the screens of the cave display down at the bottom of the screen. We had large vents that brought conditioned air into the system. The air traveled along the screens, and then they collided in the middle, creating a separation zone. And right here where the user is, the wind would actually hit the person. It appeared as though the wind was coming out of the screens. There were no fans or anything else. It created two large vortices on each side of the person that helped maintain the steady flow. So this is a diagram of the system. Really, this is kind of the opposite of something that anybody could really afford because it's becoming a larger and more complex system. It built a large wind tunnel around the person, a large fan at the back, a return plenum. We were using about a 50 horsepower fan to drive the system. We're using flow conditioning towers to supply the wind. It became more complex, but on the other hand, it's creating new technology and investigating new ways to solve the problem of extended reality. Here's a diagram of the system. Again, not very portable. A very large system, but for the sake of research, it does create new capabilities and the ability to understand new technology. Here you can actually see what it looks like from inside of the system. One of the things we heard people talking about earlier is the idea of using simulations of the real world. We use GPU-based fluid dynamic simulations to simulate the flow through the real world. We could display the particles of air flowing, and then we could control the air hitting the person to simulate the actual computational simulation of the flow. Here's a smoke visualization of the core flow actually coming along the screens and then coming back towards the person's position. You can see the two standing vortices, and here you can see the wind shifted off to the right about 20 degrees. Now, from there, we integrated olfactory display, the idea of having scent in the environment. So if you're walking through the city, you could smell the apple trees or the cotton or the cherry blossoms. And the idea was, again, that these scent particles would be delivered to the person through the vent towers over here on the side. You can see the spray nozzles. And here's an actual visualization of the particles actually flowing into the environment. Again, a laser sheet showing the flow. One of the things that we discovered, though, is that this kind of technology created time delays. It took longer to transport the flow to the person than we wanted, about 2 to 5 seconds. And it also produced latency. Odors remained in the environment. And because it was getting mixed into the airstream, it took a long time to get it out of the environment, and it created more of a ambient odor than an acute odor. So from there, we created something that we called the multi-sensory display teapot, mist teapot. And with that, we moved the scent injectors right up in front of the person. We also added mist so that as you're walking through the virtual world, you could smell things very acutely, as well as feel things like moisture or mist, like walking through the fog. Or if you're out walking this morning, you could see the fog in the air and you could actually feel it. And from there, we also incorporated a heat lamp in front of the person, and you can actually see the actual physical system. Again, it's a large system. For the sake of doing VR research, is good, but it's not something that is at a consumer level by any means. From there, we did a study with the system. The person actually went for a walk through the woods. They started at one location, they followed a path, crossed a river, they would feel the mist. And then we had a couple of different startles. We called them the bird startle, the beam startle, and the thunder startle. And the question we were trying to address is whether or not somebody with multisensory display would have a different startle response. This actually motivates from one of my other projects where we're trying to create a smart helmet to help people protect themselves from impacts. And one of the things we wanted to know is how different environmental factors might cue somebody into a startling situation or help them protect themselves. So we created a number of different startles with different levels of graphical and audio stimulation. And then we conducted a modest sized subject study, about 120 participants, and they experienced different combinations of different startles. So you can here see, for example, the bird was a very small startle. It was a very subtle object that just flew across the screen. The beam was a full screen startle where the beam would fall down as they walked through a barn. And then the thunder startle actually was a condition where when they were going into a valley, the world would become dark and cloudy. And at that point, we would change the wind, we would have mist, we would have a change in odor. Now with the bird startle, it had very subtle graphics and audio. There was no audio really tied to it. One of the things, of course, that we saw was audio significantly affected the startle response and the perception of that startle. One thing we did notice, though, surprisingly, is that environment had a notable effect on reducing back muscle activation. So if you look over here, you can see with environment off, we have higher activation level than we have over here. I should mention that we used EMG as one of our measures. We also used a survey as to how startling something was. So it was interesting. Enabling the environment actually reduced the startles. Now the beam startle, it's large graphically. It's a full graphical stimulation. And if you do research into startles, there's different ways to startle somebody. The psychologists do, audio, graphics, all the way down to electrical shock and hitting people with objects. But we're not hitting people. We're just, well, actually we're spraying them with mist, maybe. I guess that's part of it. But So one of the things that we saw here was that when we enabled the environment, it had a significant effect on increasing the neck response. Now, one of the things that we thought about this was that what this is probably doing is people are cued into their environment at this point. They're paying more attention because of the environment being enabled. When they're walking through the environment, through the virtual world without environmental displays turned on, that's going to be the wind, the mist, odors. They pay less attention, but when the environment was enabled, they were paying more attention. So what it meant was they were looking around more and paying more attention to what was going on. So they were less startled when the environment was on. With the thunder startle, it was interesting. We tried to create a premonition by changing this environmental display. And I'm a robotics person and I do a lot of teleoperation. And one of the things we wanted to know was, could environmental display help a person become more aware of their environment so that they could be less scared by something that might happen? And what we actually found is when we enabled the environment, it had a significant effect on reducing the back, eye, and survey data regarding the startle. And that includes audio. And in the psychology world, they know that if you provide a large, loud noise, people will have a startle response. It's like being in that scary movie. They can scare you with that loud noise, even if it isn't a scary scene. But what we found is when we turned on the environment, the premonition that it created, even with the loud noise of a thunder and lightning clap, they didn't respond. They didn't respond physically. You can see that the numbers are a lot lower over here for the EMG. Let's see, you can see the back is lower. You can see, I guess, eyes probably pretty similar, but the survey data is a lot lower. So with that being said, we found that the environmental display was able to reduce things a lot. Now, in terms of extended reality, we've also done work in terrain display. And what we've done here is we've created what we call smart shoes. They're a soft robotic shoe, and they actually have a series of bladders that you can see down here in the bottom right corner. And the bladders are each filled with mechatronics so that if somebody is stepping on the bladder, we can actually query where they are stepping in the virtual world using motion capture, and then say, this is the shape of the terrain where they're stepping. And then we deflate the air in the bladders as they step on it. We just open valves, and as they step on it, the shoe will tip one way or the other. I guess I should, good, I'm joined on audio, good. So what that means is that as they're stepping, we can cause the ankle to roll, cause the toes to dip in or the heel to dip in. So we did a study with this, and in this case, we were using healthy elderly subjects and Parkinson's disease patients, and we were trying to understand how the smart shoe would affect their ability to locomote. This is really a pilot study aimed at trying to understand using this technology for gait therapy for people with Parkinson's disease. So we had a couple of variations. We had them use their regular shoes, walking on the terrain that you see here. This is modeled after an actual cobblestone. And in real experiments, we actually tested the subjects, the patients actually walking on real cobblestone versus walking on the simulated cobblestone that you see on the projected on the ground. We also walked with the smart shoes inflated, so keeping the bladders pressurized, and then doing smart shoe rendering, actually rendering the terrain. And for characterization, we looked at their gait characteristics. For example, their cadence and their step length. We looked at their lower body kinematics, hip and knee ankle swing, and also user surveys. So a few key results. One of the things is we saw that the smart shoe really improves the realism of the graphics, especially for the healthy elderly. If you look over here, it was kind of funny. They just put on this different pair of shoes, but healthy elderly people all of a sudden said, wow, the graphics are more realistic, even without rendering the terrain. It was like, huh, that's interesting. Whereas people with Parkinson's disease, you know, they said it's all about the same. The second question about realism of walking on cobblestone, you can see that the rendering had a significant effect on realism for the healthy elderly, and it really pushed the envelope forward on people with Parkinson's disease too. Now, this was actually something that was interesting. The walking difficulty, just in general, difficulty of walking. You can see that healthy elderly people with regular shoes are like, no, it's not too bad. But as soon as they put on the smart shoes, they're like, oh my gosh, this is hard. And then when we did rendering, they're like, oh, this is actually a little easier. But, it's kind of interesting for the Parkinson's disease subjects. You can see that, we had a pretty big spread overall for walking difficulty, just in general with the regular shoes. But, as we added the smart shoes and did rendering, it got a little bit more difficult. And again, something similar for cobblestone. You can see that when they were walking on the cobblestone, it gradually increased. But over here, for the people with Parkinson's disease, when we were rendering all of those cobbled stones, things that would cause your ankle to roll over, something that would cause grandma and grandpa with Parkinson's disease to normally fall. They're like, wow, that was more challenging. And that was actually our goal, is we wanted to make it challenging for people with gait mobility so that they could learn to walk in a simulated environment that was virtual, but yet something where it was safe. We use body weight support harnesses. They're not going to fall. You can imagine that this is a way that you could teach grandma and grandpa once they get Parkinson's disease to be able to walk without getting injured. And again, we're really looking at trying to create physical therapy devices. This isn't going to be like the consumer device that you put in your living room. But on the other hand, if a clinic can afford $100,000 for a nice treadmill that could help prevent somebody from falling and breaking their hips and dying, that's a pretty good deal. Now, we also compared it to real world data. And something that's interesting here is that while we didn't see a significant difference in our height normalized speed and cadence, our collaborator Shu did, which was kind of cool. The reason I say that is we didn't see a difference, but they did. And when we compared our results to theirs, our results are actually pretty darn similar. If you look at some of these p-values, they're pretty high. Now, of course, we didn't do a proper similarity test, but at least we compared them. And you can see once you have a p-value of 0.99, 0.94, these are pretty similar values. So the smart shoe with the rendering actually created similar biomechanics walking in virtual reality as to walking in the real world. Now, this leads us to what we've called the MIST teapot, which is really the integration of all of these things. It's the cave display with floor projection, the 3D stereographic display, the tether forces, the environmental display, wind, heat, temperature, and odor, and then terrain display on top of that. Now, in terms of where we're going now, our current project that we're working on is a large workspace haptic display. And this is the part where I go, wow, it's perfect that I followed Manuela's presentation, because here we're trying to create simulated handles that people would interact with and manipulate in the virtual world. So it's actually pretty intentional that you see somebody here holding a cane and then walking up to a door and trying to open it. This is a two-handed manipulation task. And for a lot of elderly people, this is pretty challenging, just to open a door and walk through it, especially a heavy door. So what we're trying to do is we're trying to create these manipulators that people can use to interact in virtual reality. The handles will be at the same location in the graphical space, so that when they reach out and grab the object that they see, they're going to grab and pull open an actual door. They're going to physically interact with the door. And in terms of the last talk, the part that intrigued me is we're looking at how the biomechanics of people interacting with these simulated objects are similar to real objects. But it does bring the good point of, gosh, are they going to grab it in the same place? And that's something that I think maybe we should be looking at too. But we're looking at biomechanics at this point. The manipulator arms, we have a large translational base that allows the arms to move along the treadmill. So as people walk, the arms can follow them. And it also allows them to accommodate larger phenomenon, like reaching across the simulated door handle. We have a SCARA-like manipulator arm at the base that allows a large 8-foot reach. And then we have a dexterous manipulator at the end that allows them to grab and hold on to the different handles and rotate them. Our end effectors, we're using actual interfaces from real objects, both to gather data of the biomechanics and the forces used to interact with real objects, And then we're going to use those same handles and load cells in the virtual world. So in here, they're going to grab the handles of a real wheelbarrow, and in the virtual world, they grab the handles of a simulated wheelbarrow. These are just a few examples of people interacting with objects. We're not at the point of doing subject studies yet. So, you know, if we're lucky enough to have another workshop in another year, I'd be able to show you pictures and videos of people doing the real thing. For extended reality, we've demonstrated the ability to provide improved immersion, physical interaction, and premonition. We're seeing realistic physical interaction during locomotion. The environmental display is able to modulate responses to different VR situations and improve understandings of the VR world. And we're able to simulate interaction with virtual objects via large workspace haptic manipulators. What can this provide? Improved training, gait therapy, and teleoperation. What's next? Well, the large workspace haptic manipulators, we've got to build them, got to get them done. We're in the process of manufacturing smart shoes. We want to do impedance display of terrain, so not just different height terrain, but different softness. So for example, walking on sand or grass versus walking on concrete. And then multi-sensory display. We would need to analyze more of our data there that we have to try to understand the actual presence that's created by rich multi-sensory interfaces. Just a quick acknowledgement to the National Science Foundation. They've been very generous to us over the last 20 or 25 years, and it's wonderful. And many thanks to all of my collaborators. So with that, I think I should probably stop.
Are there any questions from the audience or the virtual audience?
Thank you so much for the very interesting talk. I really enjoyed it. So a question about the study on the Parkinson's disease patients that you mentioned. So first, I mean, did you include the PD patients with like freezing up state, or these are patients who don't have the freezing up state?
I better be careful. I'm getting feedback. There we go. I'll mute my audio. So these were subjects that were not having freezing issues. They were on a, I should probably have my physical therapist answering this question, to be honest. But we made sure that they were able to walk, that they had been treated reasonably so that they could walk. One of the things we did do is we had to put a handle in front of the people with Parkinson's disease, because they, if they didn't have the handle there, they would get nervous, like, oh my gosh, I might fall or something. So if we put the handle there, they would actually hold on to it and they would walk just fine. And one of the things that we found after doing a longer study, we didn't mention it here, was that people's cadence improved, their walking speed improved, their gait improved quite a bit. But we're still working on that paper.
So one last question for me is that, so you showed that the difficulty that when you render the difficulty level, but the realism.
Yeah, they said the realism, yeah, they said it was more realistic walking on cobblestone when the smart shoe was rendering. And they also said it was more difficult. And we expected it. You know, it's like walking through the woods when you might roll an ankle or something. Yeah. So the regular and the smart shoe inflated were just walking on flat ground. And the smart shoe rendering was actually causing the ankle to move and move around as they walked.
So when you say difficult, you compare to what? Like difficult, it's more difficult than regular?
We just did, on this case, just a 10-point Likert scale, or a graphical visualization scale. So it was really up to them to pick the relative number.
Thank you so much. Very good.
Thank you, Nikhil.
Are there any other questions? All right, let's thank our speaker.
Thank you.